All right, guys, we're going to jump into polynomial functions and kind of everything you'd want to know about a polynomial function all wrapped up into the graph, okay? So we start up with a little warm-up, sketching the general shape of the graphs of the functions below. You should know all of these. Y equals x, that would give us a linear graph. X squared, it's parabolic, or a curve. Okay, different characteristics of this curve. I don't know, symmetric, from left to right through the vertex. We call this the axis of symmetry. Both it's starting up, finishing up, decreasing, then increasing. A cubic function, x to the fourth, x to the fifth. Really all that's happening between x to the fourth and x to the fifth, as you guys are going to see, is it mirrors the shape of the squared and the cubed in terms of the fourth and the fifth respectively, okay, but it's growing faster, all right? It's thinner, it's narrower. Same thing with the x to the fifth graph, okay? So, like I mentioned in when we set up chapter 3, is that you guys know a lot about polynomial functions already. There are some things that we'll talk about here, like what a polynomial function is, how it looks on a graph, and how it certainly does not look on a graph. So we've got a lot of the very math-like definitions of what a polynomial function is. Here we go. All right. The coefficients of the polynomial are basically the numbers in front of the variables. And then we have the constant term. That's just a number with no variable. Okay. The leading coefficient is the number in front of the variable to the highest degree. And then lastly, polynomials are smooth continuous functions. And we get some vocabulary here. Okay. If we take a look at this function, definitely not continuous. Okay. It's actually smooth. It's just not continuous. There's a break here. When we have this open circle, followed by basically jumping to a closed circle on the same x value and then a continuation there, we really call this a jump discontinuity. Okay, discontinuity meaning this is the point at which the graph is not continuous anymore. How is it not continuous? Well, it's got one of those jump things going on. That's basically what that means. So we can say it's not continuous, or we can be more specific about what type of discontinuity there is. This would be a hole. Very simple, okay? Continuous to the left of it, continuous coming out of it, but a hole here. That's another type of discontinuity. Okay, so two different types of discontinuity here. If I asked you why this was not a polynomial function, you would say that it fails the continuous part. It is discontinuous. All right. The next graph, also not a polynomial function. Both of these fail the smooth category of a polynomial function. Okay. When we have a linear piece coming into a curved piece, we call that a corner. When we have a curve and then a curve coming back out, we call that a cusp. Okay, so different things for you to be aware of, different terminology. These are definitely terminology that you will see in AP Calculus or any version of calculus that you're taking next year. And then we give you a couple examples. This is a polynomial function. This is a polynomial function. Smooth, no cusps or corners, no discontinuities. Same thing over here. All right. What I'd like you to do is pause the video, and then you can type these into your calculator, if you don't mind, and then take a look at what they look like. Okay, and then we'll talk about a little bit about end behavior, which you guys talked about. All right, what happens to y as x increases and decreases, and then you can get just a general sense of what it looks like. Okay. First, degree 2, 2 zeros. End behavior as x approaches infinity. Y also approaches infinity, pointing up. As x approaches negative infinity, y still approaches infinity. It points up on both sides, basically. Degree 3, how many zeros did it have when you typed it into your calculator? It had 3. As x approached infinity, y also did. As x approached negative infinity, y approached negative infinity. Okay. Degree 4, zeros 4, y approached infinity, y approached infinity again. It was pointing up and up. And then this had 5, degree 5. Here's where I'm finding the degree. How many zeros did it have in the calculator? It crossed the x-axis 5 times. And as x went to infinity, y went to infinity. As x went to negative infinity, y went to negative infinity. Okay, and that just shows us our end behavior. Which direction is it going off to as x and y keep going further and further to the right and to the left? Okay, let's turn the page. We can make some generalizations and conclusions based on that, things that you've already known. Okay, if the degree is even and the leading coefficient is positive, okay, we're going to have end behavior that is both going up to positive infinity. If it is an even degree but negative, the end behavior will be going off to negative infinity, both as far as we can go to the right and the left. If it's odd and positive, as x approaches infinity, y will approach infinity. As x goes as far to the left as we can go, y will go as far down as we can go. And if it's negative, these flip. Okay. So really the end behavior is what the graph is doing on the ends. And those are the 4 different ways that a polynomial function can end, both on the left and the right. I know it's seemingly starting and ending, but we don't talk about graphs really starting in certain places. And the way we want you to write it is using this terminology and this notation. What is y doing as x is going off to infinity or negative infinity? And now we're going to ask you to do a couple different things when we get to graphing polynomial functions. And really, the most important thing that we're going to do is identify what type of function we have, what's the degree, is it positive, negative, and realize how to work with it to find our x-intercepts. So we'll talk about that in a second. We'll ask you for its parent function. This is a quadratic, a degree 2 polynomial. Its parent function would be x squared. Okay, so that's how we should be comparing it. The graph should look similar to an x squared graph. What's the degree? The degree is 2. How do we find an x-intercept? Plug 0 in for y. How do we find a y-intercept? Plug 0 in for x. What's the domain? All x values. What's the range? All y values in interval notation, please. End behavior. And that's x approaching infinity or negative infinity. What is y doing? All right. So let's do that for this function. This function we should not need a calculator for other than finding the range, and we'll make adjustments on that if needed. If there's a problem we don't want you to use a calculator for, we might not ask you for the range. Okay. So here's the deal. Parent function, let's plug in 0 for y. Well, let's see what happens. This just gets us a quadratic equation. Can you solve this quadratic equation by using the quadratic formula? Sure. I think easily enough we should be able to factor this quadratic equation. All quadratics aren't factorable, but this one is. X plus 3, x minus 2, x would equal negative 3, x would equal 2, and our x-intercepts are negative 3 and 2. X-intercepts are also known as zeros. Y-intercept, plug 0 in for x. That goes to 0, that goes to 0. The y-intercept is negative 6. The domain, all x values. Well, let's graph this now. We should be able to. Well, let's actually go down to the end behavior. Okay, this is an even degree, and its leading coefficient is positive. So as x approaches infinity, y approaches infinity. As x approaches negative infinity, y will approach negative infinity. Okay, so we've got all that stuff going on. All of these things will lead to the shape of our graph. Okay, so let's put our x-intercepts on first. 1, 2, negative 3, 1, 2. Now, just for the sake of kind of talking about something you already know, the vertex will be in between these in terms of the x's. So the vertex will not be the y-intercept. It would be at x equals negative 0.5 and down here somewhere. Okay. The y-intercept is negative 6. 1, 2, 3, 4, 5, negative 6. All right. The end behavior, up and up. Now the range, we would use our calculator for this, okay? The range is going to basically be the minimum value of the vertex, okay? You would see that if you plug this into your calculator, the vertex would be at negative 1/2, comma negative 6.25, or negative 25/4. Okay, so we can put that here on the graph. Okay, and end behavior, basically up and up. Domain of every polynomial function that has ever existed would always be negative infinity to positive infinity. It's smooth and continuous. It will always go off from negative infinity to positive infinity from left to right. Awesome. Okay. The last part of part 1 of this video, we're going to talk about the multiplicity of zeros. Okay. So our two zeros here were negative 3 and positive 2. And then we get into what is defined as the multiplicity of a zero. Okay. And we're going to give you the really math-like definition. If C is a zero of polynomial P, where the corresponding factor x minus c. So let's just talk about what that means, okay? Just like when we factored this and found the zeros, for every zero, there would be a factor that corresponded to it to basically tell us how we got that zero, or vice versa, if you want to think about it the other way around, okay? This factor led to this zero. If I told you that this was a zero of the polynomial, you should know that this factor will be in the factored form of that polynomial. Okay? If c is a factor, where if c is a zero and the corresponding factor x minus c occurs exactly m times in the factored form of p. Okay, so if we had the polynomial in its factored form, m is how many times this factor occurs. Then c is a zero with multiplicity m. And m is the multiplicity. Okay, very simple. All right. For example, if we had f of x and we either gave this to you in factored form or you were able to factor it, and this is what the factored form of the polynomial looked like. Okay. Let's say it was a 6th degree polynomial. When we factored it, we got x plus 1. We had x minus 3 show up 3 times, and x plus 5 show up 2 times. Well, obviously there's a 1 here. These represent the multiplicity of each one of these factors and zeros. And why do we need to know that? How is it connected to the graph? An odd multiplicity, the graph crosses at that 0. If it is an even multiplicity, the graph bounces at that 0. And let's show you how that might look in this graph. Zeros of -1, 3, and -5. Okay, so at this 0, multiplicity 2, it's going to bounce. Now this is 6th degree, even, so we're going to be up and up. It bounces off this one, okay? It would then cross sorry, where's the -1? It's going to cross at -1, and then it's